Automation has affected our lives in profound ways, but when it comes to air transportation, the benefits of automation are yet to be fully realized. We are still moving things around as if it was 30, 40, 50 years ago. We started Reliable Robotics back in early 2017. We acquired a Cessna 172 to first prove to ourselves that we could actually automate a plane through all phases of flight. We got FAA approval to demonstrate fully automated operation, and eventually we got to the point where we pulled the test pilot out of the plane and demonstrated unmanned flight.
Unmanned Cessna is turning left downwind for 3-1, Hollister.
The unmanned flight was our arrival. We kind of realized, hey, we've finally completed a safety critical operation and we've done something that nobody else has done before, and we've done it in record time. The greatest achievements for Reliable Robotics in 2020 circulated around our ability to apply all the knowledge that we had from the 172 program on the 208. In order to develop the remotely operated aircraft system, we don't just focus on a single piece. Reliable Robotics works on software, simulation, hardware, avionics, actuators. We bring it all together to deliver the end-to-end package. In order to meet all the regulations that we have to for an end-to-end autopilot system, there is a large amount of certification and development that gets approved and needs to be adhered to very strictly to actually bring this product to market. And on the 208, that's the challenge.
You need to be able to trace everything that you're doing back to the regulations. Every line of code, every physical system that you install in the aircraft, you have to be able to trace that to a test case, to implementation artifacts, to a design document, to an FAA acknowledged piece of guidance, whether it be a standard or advisory circular, acceptable means of compliance, and then finally a federal regulation. We've developed in-house a set of software tools that are web-based that allow any engineer in the company to go through from a design and trace that all the way back to the federal regulation.
Probably the biggest challenge with the 208 as an automation project is the overall complexity of the system. It is a relatively simple airplane, but there's still a lot of function that the pilot performs in the cockpit. Applying actuation and automation to all of those functions is actually quite extensive. We've tried to pursue industry standard, available off-the-shelf actuators, but we found that a lot of the hardware that was out there didn't meet the level of reliability and redundancy requirements that we had, or they didn't include the clutching mechanism that we required. So that did push us into designing our own actuators. With our actuators that we've installed, it is an in-house design, so it didn't come with a suite of test reports. We've built test stands to do static testing, dynamic testing, engagement, disengagement of clutch system, endurance testing, thermal testing, vibration testing. By the time the actuator is going into the airplane, we have exposed it to well more than what it will experience in a normal flight operation. We can trust that it's going to continue to function as required.
One key achievement for us was on the navigation side. Currently, if you want to land an aircraft automatically, it relies on ground-based assets.
We're building a system that can auto-land a Part 23 aircraft at any airport without any ground infrastructure. The main challenge to achieve that is to take existing hardware, pair that with novel navigation algorithms and multiple layers of fault detection to achieve the integrity required to perform that auto-land function. The Reliable Robotics navigation system achieves accuracies that allows the aircraft to land within feet of the center line.
The thing that sets apart the Reliable Robotics Autoland is that we've worked with the FAA through white papers to make sure that we're building the correct approach to doing an autoland with any aircraft in any airport.
On the avionics front, we were able to achieve key milestones as well. One of the main items there is having a low-cost, reliable flight computer. To be more exact, a system of flight computers, because a single flight computer does not have the reliability that you need to fly the vehicle. So we developed a system of flight computers that can share states with each other, be synchronized, and function in the presence of any device failing at any given time.
We believe a system such as ours is going to make aircraft dramatically safer, because when there is an issue, our system will not only recognize it faster, but it will be able to respond to it faster.
We have stood up a system that we can fly our aircraft virtually in our simulation. That is a full 6 degree of freedom simulation that represents the aircraft and all of its environment. With that, we can fly contingency cases like extreme crosswind, extreme tailwind, off-nominal wind shear conditions, or we can fly at real high altitude and low altitude. We can fly with CG front, CG back. Allows us to show that our aircraft is stable and performing as we expect it to be.
A simulation is basically just emulation of the whole airplane. What happens in the real world is what you want to emulate when you talk about simulation. Just because the hardware is extremely reliable or the algorithms are very novel doesn't guarantee safety. What brings safety together is obviously all of these pieces coming together and then being able to put all of those things, how they behave exactly in the simulation together. So if you get that part exactly modeled right, then effectively you're doing exactly what's going to happen on the day of the flight.
When we demonstrated automated landing on the Cessna Caravan, we did over 140,000 landings in simulation. We successfully landed on our 3rd day of flight testing. And what we saw in reality matched very closely to what we had devised in simulation.
Our system not only allows us to fly the aircraft safer, it also allows us to fly the aircraft more efficiently. In our system, we can optimize for the proper amount of fuel burn because we can tightly control how fast we fly, our climb rate, where we fly. We're consistently flying exactly the route that we want to fly.
There's no one out there that's doing auto taxi, auto takeoff, en route flying and then landing. Putting all of that together and then not only being the developer of the technology, but also the operator of it is unique.
We've very deliberately built a group that has the right mix of Part 23 and Part 25 certification experience with people that have built other types of advanced automation systems elsewhere in aerospace, robotics, and autonomy. In the future, we're going to see use cases for automation that I don't think we're even going to be able to imagine today.
Once you have proven out the technology in the cargo space, you can take it to the passenger transport level. Currently, how airplanes are functioning is if you want to fly to a location, Southern California, you take a pre-scheduled flight. If you want to fly to a more remote location like Lake Tahoe, there's a regional municipal airport in that area, but that is not getting served by commercial air transport because the demand is not predictable.
We currently have over 5,000 airports available today in the United States for public use. Of those, there's only about 130 that are used on a regular basis for commercial air travel. But with automation, we can eliminate the hub and spoke model and we can take people directly point to point between the places that they want to go.
People who normally wouldn't have access to flying because they're nowhere near a large airport, now they'll actually have access to be able to do that.
The goal of reliable robotics is to create a new type of airline, an airline where pilots are stationed in control centers. This will enable safer operations, more efficient operations, and will ultimately make air transportation more accessible for everyone.